Okay, so this is 2018 FRQ number 4, and it says the height of the tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Select the values of h of t are given in the table above. Okay, use the data to estimate h prime of 6 using correct units. Interpret the meaning of h prime of 6 in the context of the problem. So we want to find the derivative of 6, and you can see that 6 is right here between the 5 and 7. So in order to estimate the derivative, it is really another way to say slope. So I'm going to use y2 minus y1 over x2 minus x1. So h prime of 6 is equal to 11 minus 6 over 7 minus 5. So that's 5 over 2, 2.5. So what does that mean? That means at year 6, the 6th year, right? The tree is growing at a rate of 2.5 meters per year, right? Because that is the slope at that point, so that is the rate at which it is growing. Okay. Part B, explain why must there be at least one time from 2 to 10, so between 2 to 10 years, where h prime of t equals 2. So this is where mean value theorem of derivatives comes in, right? It's saying that, hey, is there a time where the slope is equal to 2? Because if the slope is equal to 2, then there must be an instantaneous rate that is equal to the average rate, right? So let's see, is there a slope that's equal to 2? So it does take a little bit of guess and check to see which interval will give you the 2. But if I see it correctly, it's this interval right here, because 6 minus 2 is 4, over 5 minus 3 is 2, so 4 over 2 is 2. All right, so for part B, you can say that h of 5 minus h of 3 over 5 over minus 3 is really 6 minus 2 over 5 minus 3, which gives me 4 over 2, which is 2. So by mean value theorem, there must be a C, or h of c, where h prime of c equals to 2. Okay, so that's it. Yeah. All right, moving to part C. Use a trapezoidal sum with 4 subintervals indicated by the data to approximate the average height of the tree over a time interval between 2 and 10 years. So this is the mean value theorem of integrals, right? So we're going to take the area using trapezoidal rule to approximate it, and then we find the average, right? So let's see if I have more room down here. Yes, part C. I do have to jump back and forth. All right, so trapezoid. So let's see, are these all uniform width? They are not. So I would suggest you to just to use the trapezoid rule, but calculate each trapezoid at a time, because these intervals here are not the same, right? So if you use the formula of just one height on the outside, it's not going to be very helpful for you. So I'm going to look at the first two. This is my base 1, base 2, and the height is the difference between these two, right? So by trapezoid, 4 subintervals, right? So that's equal to 1/2 base 1, so 2 plus 1.5 plus base 2 times the height of 1. Okay, next one, 1/2. Here's my base 1 and base 2, 6 and 2. 6 plus 2 times the height. The difference between 5 and 3 is 2. And then next one, base 1, base 2, 6 and 11. And between 5 and 7, the height of 2. And last one, the height, base 1, base 2 of 11 and 15. 11 and 15, height of 3. Okay. All right, so that gives me 1/2 times 3.5 plus, I can reduce these out, so plus 8 plus, reduce these out, 17 plus, okay, so 1/2 times 26 times 3. All right, so that's a little bit easier. 3.5 divided by 2 is 1.75. 8 and 17 is 25. And then this reduces to 13 times 3 is 39, which gives me 1.75 plus 64. So 65.75. So that's the trapezoid rule, the sum of it, right? But we want to find the average. So don't forget the average is between 10 to 2 years. So it would be 1 over 10 minus 2 times 65.75. So that's 1 over 8 times 65.75, right? So you can divide it through. I think I did. So 65.75. Yeah, you can't use a calculator, so you really got to do this by hand. Is there a quicker way? So this is where fractions may come in easier, right? So if you had kept this first piece as a fraction, you would have known that that first piece would be 263 over 4. So that would give you 263 over 32. That would be your average, right? But if you did not, you can still divide this out. So if you do 65 over 75, you have 8, it's 8, 64, 17, 2, 16, 15, 1, 8, this is 7, add a 0, 60, almost there. So 5. So that will be your answer, 8.21875. So that could be your alternate answer to part C. Okay. All right. Last one, the height of the tree in meters can also be modeled by the function g given by g of x equals 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meters per year. According to this model, what is the rate of change of height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? So you can see with respect to time, this is a related rate problem. Okay, all right, so our g of x, this is part D, our g of x equals 100x over 1 plus x. Okay, so with g of x equals 100x over 1 plus x, first thing we want to figure out is when the tree is 50 meters tall, what is our x? What is our diameter? Okay, so let's find out the diameter first. So we get 50 equals 100x over 1 plus x, so there's only x's left, right? Cross multiply 50x, 50 plus 50x equals 100x, 50 equals 50x, x equals 1. So when the tree is 50 meters tall, the diameter is 1. Okay, so g of x equals 50 when x equals 1. So that's something to remember. And then you also know that the diameter of the base of the tree is increasing at 0.03 rate. So the diameter is increasing, right? So dx dt equals 0.03 meters per year. Okay, so we're looking for what is the rate of change of the height with respect to time. So we're looking for dg dt, right? So here's a problem. You are looking for dg, change of the height according to time, but the height is based on the diameter. So that the height g is dependent on x right now, and then x is dependent on t. So you have to take the two derivatives. So essentially you want to take dg dx and dx dt, so you can get what you want, which is dg over dt, which is the rate of the height with respect to time. It's a little convoluted, so it's a little bit weird, okay? So we're going back to this original function here. And we're going to take d dt of g of x. And how you do that? You take d dx of the function, because this is with respect to x, right? And then you multiply by dx over dt. That way you can get d dt. You can get the d dt by itself. So you can do the, sorry, let me try to do this again. So you can take the derivative of what's in the parentheses with respect to the x and then multiply by dx over dt. That way you can transform it into a dx over dt function, okay? All right, so 100 over x, you want to use quotient rule. Oh, I'll make sure I have room for this. So d dx, so you have low d high minus high d low over low squared dx dt, okay? So multiply this out, you get 100 plus 100x minus 100x, woohoo, all over 1 plus x, 1 plus x squared, because I'm happy these will reduce out. So we really have d dt of g of x equals 100 over 1 plus x squared dx dt, right? So that's what we're looking at. Now let's look at everything we have so far, right? So we have on the right hand side, we know x is 1, and we know that dx dt right here is 0.03. So let's plug in everything we know. So that's 100 over 1 plus 1 squared times 0.03. So 100 over 4, 0.03. So that's 25 times 0.03. That's 0.75, right? So is it 0.75? 100 over 3. Yes, 3/4. I am right. So when the tree is 50 meters tall, this is the rate of change. The height is changing at 0.75 meters per year. Okay. All right. That's it for this problem.